So we're trying to put branches on benzene, which we've seen is a poor nucleophile. In the mechanisms for bromination and for sulfonation, the first step is always recognizing that benzene is a nucleophile because it has those pi bonds, but it's very stable, so it's not very reactive, so it's a poor nucleophile. And in order to tempt it to react, we have to combine it with an awesome, amazing, incredible electrophile. Preferably one that has a full positive charge rather than the partial positive charge. And so there are different ways to get that amazing electrophile. And in this one, what you need to do to get it is to add sulfuric acid to nitric acid. So if you take benzene and you mix it with nitric acid, which is a strong acid, and sulfuric acid, which is another strong acid, those two acids together are actually strong enough to dissolve gold if they're combined. And you put them together with benzene, it doesn't dissolve the benzene so much as it puts a nitro group on it. So you end up with an NO2 nitro group. Okay, well, what's happening here? The first step is just to draw these things you're mixing with the benzene. What do those things even look like? Well, nitric acid is kind of weird looking. You have the nitrogen bonded to 3 different oxygens. It's double bonded to one of them. And one of the oxygens has a hydrogen, but the other one doesn't. And so you end up with this molecule that has 2 charges right next door to each other, which looks a little weird. You might even think, because here you have that positive charge in the nitrogen, because it's bonded to 4 atoms, and then the negative charge in the oxygen. So you might even think that that wouldn't form, but the reason, of course, why this is stable is because all of those lone pairs are allylic, and so really the negative charge doesn't exist just on that atom, and the positive charge doesn't just exist on that one. There are p orbitals on each one of these, and all those charges get spread out over the whole thing. And it's because of that resonance stabilization that this is a strong acid. If the hydrogen tries to leave, the electrons as an H+, the electrons in the bond stay on the oxygen, and those get spread out through that resonance, all those parallel p orbitals. So that stabilizes it, and that's what makes it a strong acid. So nitric acid. The other thing was sulfuric acid, and we've seen before how sulfur has those d orbitals. We saw that with sulfur trioxide in the mechanism for sulfonation. So it's able to have more than 8 electrons around it, because they're not just fitting into the s and p orbitals, as we talked about in the video for the mechanism of sulfonation. And this sulfuric acid is a strong acid for the same reason that nitric acid is a strong acid. When the hydrogen tries to leave without taking its electrons with it, right, an acid is an H+ donor, those electrons in the bond end up becoming a lone pair, and that lone pair is stabilized through resonance over all of the atoms except for the other hydrogen, because these will exist in a p orbital. There are p orbitals here for the pi bonds, and then the lone pair here, one of the lone pairs also exists in a p orbital. So that negative charge there is able to be spread out over the whole molecule, and so the hydrogen can leave because it leaves behind a really stable conjugate base. And you might even notice that in the case of nitric acid, the negative charge that's left behind when the hydrogen leaves is allylic to only 1 pi bond. Whereas in the case of sulfuric acid, the negative charge that's left behind is allylic to 2 pi bonds. And so that's the reason why sulfuric acid is actually a stronger acid than nitric acid. Let me just draw those out really quickly so you can see what I'm saying, because it's going to end up being important for the mechanism. Remember, an acid donates H+, that's hydrogens without their electrons, so those would have plus charges. And the electrons that were in the bond, those end up becoming a lone pair. In the case of nitric acid, that lone pair is allylic to just 1 pi bond, so it's going to be spread over that, but this one is allylic to 1 and 2 pi bonds. In other words, it gets to be spread out over more atoms. I mean, in both cases, you have another oxygen that it's being spread out over. But in the case of sulfuric acid, the negative charge is spread out of more atoms, spread out over more atoms, which means that is more stable, which means the H plus will get away more often. And so H2SO4 is more acidic than HNO3. Okay. So what happens when you combine them? Well, if the word acid is really a relative thing. Something is only an acid if it's the strongest acid in the container. Otherwise, it'll act as a base. And in this case, nitric acid is the weaker acid here. So in this case, that oxygen on the nitric acid will act as a base and accept the hydrogen from the more acidic sulfuric acid. Now, that hydrogen can only form one bond, so the electrons in the bond that it already has go to the most electronegative place nearby, that oxygen. And so you end up getting, you have your nitric acid, the oxygen on the other side didn't change, double bond to the oxygen didn't change. You still have that hydrogen there. One of those lone pairs, though, turns into a bond to the hydrogen. And so this oxygen now has a full positive charge. It still has that negative charge there. And for the sulfuric acid, it basically stays the same, except the hydrogen is gone now. And that bond there turns into a lone pair. There were two other ones there. Full negative charge that gets spread out through resonance. And so this actually has turned what was a terrible leaving group into a wonderful leaving group. Remember, you can tell a good leaving group because if it pops off of a molecule, it's stable. If an OH pops off of a molecule, it's not stable. It has that full negative charge on a small atom, and that'll react with the first thing it comes across. But if this H2O leaves a molecule, that's really stable. It's a water molecule. So it's a good leaving group. So you can assess how good of a leaving group something is by thinking about how stable it is when it comes off of the molecule. The water is a really good leaving group, and so it ends up leaving the molecule. Now it gets the push to do that because of these charges here. The negative charge is attracted to the positive charge, so the lone pair there goes to form a double bond to the nitrogen, and that kicks this good leaving group off. So you end up with something kind of like carbon dioxide, but with nitrogen in the middle instead. And the nitrogen has a full positive charge. And that is going to be our amazing electrophile that we'll have benzene react with. So we can take that amazing electrophile, which is called a nitronium ion, and we can react it with benzene. So benzene has those three conjugated pi bonds in a ring. Because you have those pi bonds, this is a nucleophile. We have our fully positive charged electrophile here, and so we have nucleophilic attack. The pi electrons go in, attack the nitrogen. Nitrogen can only have 8 electrons around it, so if you're forming this new bond, it needs to break one of the bonds that are already there. So one of those bonds break and the atoms go in the more electronegative atom, so the oxygen in this case. So you end up with the nitrogen. It still has a double bond to one of the oxygens, but the other oxygen will be a single bond, and that oxygen, these both had 2 lone pairs to begin with. This other one will now have 3, that third one was added. Those are the electrons in the bond, and that has a full negative charge. The nitrogen still has a positive charge. The overall charge on that is 0. So we have that. Next thing to notice are these electrons in the ring. Those were shared between 2 carbons, but they ended up just going on one of them. So the other carbon is missing electrons. It has a positive charge. And another thing to follow is just the hydrogen that was here. We're going to follow that through its life course. So we have this intermediate, and this molecule is actually a resonance structure. You would know it's a resonance structure because you have a positive charge that's allylic to a pi bond. It's one atom away from an atom in a double bond. And because of that, that means you have those parallel p orbitals. The positive charge is an empty p orbital. You have two parallel p orbitals for the pi bond, so the electrons can spread out over that whole region. And so it's misleading to say this is a double bond, these are single bonds. The electrons are actually spreading out. So to show that, we'll draw resonance structures. Now we warn the world that none of these structures are true. The true structure is only, ever, always the average of everything. We warn the world by drawing those brackets. Between the brackets, we tell everyone take the average by drawing that special resonance arrow, one line and two heads. Not to be confused with the equilibrium arrow, two lines, each with one head. Equilibrium means reactants are turning into products. Products are turning into reactants at the same time. Resonance means neither of the structures on either side of this are true. The true structure is only ever the average. So we would end up getting this other structure. When you have an allylic positive charge, you draw the other resonance structure by moving the pi bond toward the positive charge to create a new bond there. And so if that moves over, you end up getting the pi bond here, and the positive charge will be on the bottom carbon. This carbon had these electrons on it, and it doesn't anymore, so it has the positive charge. That positive charge is allylic to two pi bonds now. It's allylic to this pi bond on the right, but if we draw the resonance structure for that, we'll just get the structure already on the left. So to draw the different one, we'll look at the fact that it's allylic to that pi bond on the left. So to draw the resonance structure, you move the pi electrons toward the positive charge, right? Because these have these two parallel p orbitals. This positive charge is an empty p orbital, so these electrons can fly over that whole distance. So we'll represent that by drawing another resonance structure. We say take the average, and when you do that, the positive charge will go away, this bond will move, and this carbon at the top that had those pi electrons doesn't anymore, it's missing them, and so it has a full positive charge. So that resonance stabilized intermediate is called the sigma complex. It's the only reason why benzene will even react with a strong electrophile. Because this is so stable, you'd have to really get it energetic in order to create an intermediate. The fact that this intermediate is also pretty stable because of all of this resonance means that it's easier to form it. So we have that, and it's relatively stable because you're spreading the charge out through all that resonance, but it's not perfectly stable because you've destroyed the aromaticity of the ring. So you want to recreate that, and so we need a base. We need a base to steal this hydrogen. And we've seen this in the example of, and we've seen this in bromination and in sulfonation. In bromination, we had the bromine with the negative charge attacking that hydrogen to restore aromaticity. In sulfonation, we had water attacking that hydrogen to restore aromaticity. So here, what we're going to have is the conjugate base of the sulfuric acid. That comes back, that's missing its hydrogen, and so it can get it back just by attacking it. The hydrogen goes to form the aromaticity again. The electrons go back to form the pi bond that restores aromaticity. So you end up with the benzene ring, aromatic, with the nitro group on it, notice This all adds up to a charge of 0, even though those two atoms have formal charges on them. You end up with that, and you end up with sulfuric acid. So sometimes this structure on the left, nitrobenzene, that's just written as NO2. Those are the same. And also notice with the sulfuric acid, we started with sulfuric acid at the very beginning. We end with sulfuric acid. So the sulfuric acid is not used up. A molecule that lets a reaction happen but doesn't get used up is a catalyst. So here the sulfuric acid is acting as a catalyst. And the windup is that we put the nitro group on the benzene. So just to review what we did really fast. First, we made an amazing electrophile, full positive charge. We mixed nitric acid together with sulfuric acid. We saw that sulfuric acid is more acidic because the negative charge it leaves behind is stabilized through resonance with 2 pi bonds. That turns a bad leaving group into an awesome leaving group. The opposite charges here neutralize each other out, kick the leaving group off, and you form the amazing amazing electrophile. That tempts benzene into reacting. Benzene attacks the awesome electrophile. You get your resonance stabilized sigma complex, and then a base. Here they're showing water, and if you want to use water, that's completely fine too. You have the water that was kicked off of the nitric acid. That could act as a base. You could also use the conjugate base of the sulfuric acid, whichever one you want. You have that base taking off the hydrogen and restoring aromaticity. And that is the nitration of benzene.